Okay, good morning, everyone. Okay, so welcome to another lecture. All right, so last Friday, okay, you all came to the lab and managed to draw all your stuff. Okay, so I will be sending out a poll later. Okay, after the lecture, for those students who still have not formed a group. All right, then you can help me to fill up the poll. And based on the lab group that you belong to, I will either pair you all up to or group you all up together or join you all with some other existing team. Okay, so just make sure that those of you who already have a team, please make sure you register in Luminous. Okay, so if you're not registered in Luminous, then you still do not belong to any team. Okay, so for the board that you collected, like I mentioned, you can do the soldering probably this week. Okay, and you only need to solder one board. All right, so you can so in your team you have maybe 3 or 4 boards, right? You just solder one of the boards and use that board for the development work. Okay, hopefully that one board lasts all the way. Okay, but if it gets damaged or whatever, then you can switch to another board in your team. All right, so you just need to solder one of it. All right, and I will later show you. Probably if you just want to solder a part of it, all right, you can for the next week's lecture, I will update you all how to go about doing it. All right, so next week is of course Chinese New Year week, so we don't have the lecture. Okay, but I will tell you what's the plan later. Okay, so let's get started. Okay, so we'll be having a new lecture, a new topic on the GPIO. All right, so everybody can see my screen here. Yes, okay, thank you. Okay, so so the first few lectures, like I said, is things that you have been exposed to before, but probably in a different platform. Okay, but we just want to go a bit deeper, okay, and look at it in the context of this controller, and at the same time, you know, pick up some good techniques and skills, not only the programming part, but also how to extract information from the data sheet. Okay, how to write more efficient code and things like that. Okay, so GPIO is again nothing new to you. Okay, so let's get started and see how we can actually configure the GPIO pin on the KL25Z board that we have. Okay, so we are going to go through a simple example. Okay, but of course, the simple example is just the LEDs and switches. But before we get to that, we still need to understand the whole mechanics behind how the GPIO module in this particular microcontroller is configured. All right, and then how we can interface it correctly. All right, so this is the hardware that we're going to be sort of discussing. All right, so we have a switch over here, okay, connected in this manner, and this is the pin connected to the microcontroller, and at the same time we have 2 LEDs. All right, which we need to drive. All right, so this is a simple setup. All right, so let's first have some understanding, okay, on how this hardware is configured. All right, so can you all submit your replies, okay, to the pollev.com. Just open up any browser. All right, so the question here is what kind of pulse will be observed at the switch in? So this switch in is basically the input of the microcontroller. Okay, so this is the input of the microcontroller. So when I press the switch, okay, okay, maybe I should say as press and release. Yeah, correct. So when you press and release the switch one, what kind of a pulse or signal will be observed? Okay, so again, even though we have gone through such things in the EPP1 before and EPP2 before, still there is always some confusion. All right, so it's always good to clarify even these basic concepts, because again, as computer engineers, you need to be well versed with the hardware and the software. All right, so if either side does not sync up together, then the system is not going to work. Okay, so I think about half of you have replied so far, and the general answer is a negative going pulse. Okay, so let's just confirm and see whether this understanding is correct. All right, so let me go back to the previous slide here. Okay, so over here, what we have is the switch, okay, that is connected. Okay, so if you look at this switch, so this is the pin, the GPIO pin, okay, and it's pulled up to through a resistor to your VCC, let's say plus 5 volts. Okay, if I just put it as plus VCC, okay, and then you have a switch over here. All right, now by default, okay, if you look at it by default, if I do not press the switch, the GPIO is actually pulled up high. All right, so by default, the voltage is a high voltage, okay, or a logic 1. Okay, when I close the switch, okay, when I close the switch, what happens? I create a short circuit pathway to the ground. So when I close the switch, I actually go low. All right, and when I release the switch, again, it goes back to the default state. Okay, so this is the correct answer. All right, so again, the way we connect the switch, okay, we can connect in many different ways. Correct, I can change things around, and it can be a positive going pulse and so on. All right, so it's as long as you understand how I connected the switch, and in your software you are trying to capture the correct thing, okay, then it's fine. All right, so as long as you know the hardware and the software matches the hardware, then you should be fine. All right, so I think majority of you got this correct, which is good. Okay, so those of you who are still not sure, okay, hope that now it's a bit clearer, okay, and you understand how the switch is configured. Okay, let's do another poll. So you just consider active high, active low, okay, based on what we just saw. Okay, so this is again quite obvious already, correct? Because when I press the switch, it goes low. So the active state of the switch is considered a low logic. All right, so that's why I call it active low. Okay, so again, these are common terms you might see in books or references. So it's always good to know what are they talking about. So it's basically referencing the active state. So when I say the switch is active, means the switch is closed. All right, so when the switch is closed, the voltage I expect to see or read is a low voltage. So that is why we call it a active low switch. All right. Okay, so this next question, are the LEDs configured to be active high or active low? Okay, so again, majority say active high. Okay, again, let's look back at the circuit. All right, so if I look at the circuit over here, the positive of the LED, that means the anode is connected to the GPIO pin, and the cathode is connected to ground. All right, so the moment you know the cathode is connected to ground, that means the only way I can drive the LED is if I provide a logic 1 over here, a high voltage. Okay, then the current will flow and the LED will light up. All right, so that is basically the way to understand the circuit. So since I need to provide a high voltage to turn on the LED, then we say this is an active high configuration. All right, so majority of you got it right, so it's good. Okay, so again, all this comes back to the same understanding that you must know your hardware to make sure your software is written correctly. All right, so let's go on to the ports now. So the KL25Z has a bunch of ports over here, port A to port E. Okay, but not all the port bits are available. So this is quite common. So even if you go back to your Arduino Uno, we saw the same thing, right? Even though your microcontroller may have a lot of port pins, not everything is brought out. Okay, because you are limited by the physical size of the chip, so there are only so many pins that are brought out for connections. Okay, and at the same time, you also know that in a microcontroller, almost every pin is multiplex. All right, so you must think carefully, okay, on the different pins that you want to use. What are the multiplexing options available? Okay, and what are the trade-offs that you have to consider? Okay, so these are all the things you need to look at. Okay, so now this is just to make sure that all of you have downloaded the data sheet, okay, from the Luminous. Okay, so can you open up the data sheet, okay, of the microcontroller, okay, and tell me the page number of the GPIO section. Okay, so if you have not downloaded, now will be a good time to do so. Okay, so this is the comprehensive full data sheet, okay, from the microcontroller. It's about 807 pages. Okay, so can you download if you're not done it yet, and tell me which page or which section talks about the GPIO configuration and setup. Okay, so some saying page 99. So let's go to page 99 and see. Is it page 99? Okay, so page 99 is okay, giving you some information on the GPIO. All right, but it's just overview only. All right, but in terms of the actual configuration of the registers and everything, okay, if you just scroll the chapter, okay, if you go down, all right, you will see there is this chapter 41, okay, general purpose input output, okay, which is in page 771. So it's correct, huh? Those who put 771. Okay, so of course the GPIO can be mentioned in a few places in the data sheet, all right, but when you want to learn how to configure a peripheral, what are the registers involved, you need to go to that particular chapter that is dedicated to that peripheral. Okay, then they give you all the details and all the features. All right, so again, this is of course I keep emphasizing this from, I think, whoever has been in my class before, that the data sheet of any microcontroller, any subsystem, any sensor, anything that you want to interface, your data sheet is really, really important. Okay, many times we choose not to look at it too much, but a lot of information that is important, that is critical, is always inside there. Okay, so always make it a good habit. Okay, when you deal with a new controller, a new peripheral, anything, always try to get the data sheet. Okay, and keep it as a reference, because whatever you want to find out, okay, should be somewhere inside there. Okay, so that is why you always need the data sheet ahead. Okay, so now, okay, these few slides here are from the data sheet, all right, where I've extracted the important information. All right, so let's look at the GPIO and try to understand a bit of how it is designed. So the GPIO itself, the pin that we see is only a single pin. Okay, so whichever port, whichever pin, we only see a single connection that is available to the outside world. Okay, but internally to the microcontroller, you can see that there are a lot of internal connections and registers involved to decide how the pin operates. All right, and at the same time, there are also a bunch of registers associated with them. Okay, so if you remember from your EPP2, okay, when you deal with Arduino Uno, same thing. We had a data direction register, you have a port register, you have a pin register, and so on. Okay, so similarly, every microcontroller has its own set of registers. All right, and all of this is given here. So you can see that the registers are mapped to specific addresses. All right, and these addresses later, when we look at the software, okay, the kit IDE, I will show you how it is defined there. So all of this needs to be properly defined in the header files of your kit IDE. Okay, but because the kit IDE already supports this microcontroller, okay, when you create the project, everything is already automatically included. So we don't need to manually go and do all this. Okay, but I'll show you where it is defined so you understand the idea behind it. Okay, now before we go on to understanding the registers, okay, if you look in your data sheet, okay, we look in your data sheet here, Okay, so if you look at it, all the ports, port A, port B, port C, and so on, all have the same bunch of registers. Okay, and what I want you to notice is this part over here. Okay, so let me let me crop this out here. Okay, so if you look at this, okay, what do you notice? You notice that for example, port B, these are all the registers involved. Okay, up to here. And then port C also has the same bunch of registers. So it's always the same sequence, PDOR, PSOR, and so on. But what I want you to notice is this. Why is there a gap over here? Okay, because I know that I need to use this many number of registers. So this is the amount of space I need. So if my last register for each port is at 54, so I end at 57. So I could easily start at 400F F058. Okay, 4 bytes away. I can easily start there. Why do I leave such a big gap and start at 80? Okay, so if you look through a data sheet, there's always a big gap between each section of port registers. All right, but why do we want to do this, or why do the manufacturers want to do this kind of a gap? Anybody has any idea? Okay, so reserve for other functionality. Okay, but what other functionality? Okay, so the answer is sort of correct. Reserve for other functionality. All right, but this other functionality is currently okay. So the reason why they want to keep this gap is for future expansion. All right, that means they want to keep the current design as much as possible, but when there is an upgrade available, they want to minimize the changes. All right, so imagine that now they release this chip, correct? A few months later, there is an upgrade available, and they want to add a few more registers to each of the port. Okay, if I start from F058, what happened? Then there is no space for me to add on more registers. Alright, whereas if I leave a gap, there is always some room to grow. Okay, so I can always add on more registers for each port, okay, along the way if there is any future upgrade to the design. Okay, so it's sort of an economical decision, right? Because you do not want to redesign the whole memory map and all these addresses and change everything just because you want to add one new register. Okay, but by designing it this way, you don't need to really modify a lot of things. Okay, but yet you can provide an upgrade very easily. Okay, so it comes down to this kind of a thinking. All right, so this is quite common. So in most microcontrollers, you always see gaps in the address space. All right, and these gaps are for future expansion, which they sort of reserve, okay, and keep it available upfront. Okay, so these are all the registers. Okay, so we will be exploring these registers along the way now. So the first register is the PDDR, okay, which is the port data direction register. So this is quite straightforward. Input is 0, output is 1. All right, so you just configure the direction of each of the pins. The next one is writing to it. Now, when I want to write to it, there are actually a few different options available. Okay, so if I want to directly write a value, I can use the PDOR register. So when I use the PDOR register, I can write a 1 or I can write a 0 directly. So whatever value I put, that value will be available on the port pin. Okay, then there are a few other options. One is the toggle option. So every time I write a 1 to it, I will toggle the output automatically. So if I write a 1, from 1 it will become 0. If I write 1 again, from 0 it will become 1, and so on. So every time writing a 1 to it will toggle the output. Then there is also a PCOR and PSOR where you can specifically use it to just write or clear the output or set the output. All right, so these are just different options available for you to change the value. All right, if you do not want to use any of it, you can just stick with PDOR. It also works just as well. Okay, when I configure the pin as an input, okay, then I need to read from it. Okay, so to read from it is the port data input register. Okay, so I need to read from it. So basically, you can see here that over this side, okay, all these are the internal sort of selection multiplexers and buffers and so on that are internal to the controller. Alright, so when we are configuring these registers, we are actually sort of setting all of this, either latches or multiplexers and so on, so that the behavior is as what we expect. Okay, so let's look at this pseudocode. All right, basically what we want to do is we want to configure some outputs, okay, for the LEDs, then configure, okay, this is for the LED, and configure input for the switch. All right, and then from there we want to check whether the switch is pressed. So if the switch is pressed or not pressed, so if it's not pressed, okay, so if you remember just now we said it is active low. So if the value is 1, that means it is not pressed. Okay, then I light up LED 2. If it is pressed, then I light up LED 1. Okay, so that is the sort of pseudocode of what we want to achieve. Okay, now let's look at the definitions that I mentioned just now. So inside the KL25Z, all right. Okay, so let me switch over to the software side. Okay, so let me zoom in a bit here. Okay, so here you can see the definitions. So inside your project, okay, when you do lab 2, okay, we are going to create a project from scratch. So in lab 1, we just opened up an existing project just to run it to see whether the board is working. So lab 2, we're going to create a new project. Okay, and subsequent labs, you're going to just repeat that process whenever you want to create a new project for the lab. Alright, so when you create a new project, one of the header files that will be automatically included in this one, the mkl25z4.h. So this header file contains all the definitions for all the peripherals that we are dealing with. Alright, so what you have here is basically the structure that is defined, alright, to manage all the registers associated with the GPIO type. Alright, so inside the code, all right, basically what you have is you have this, okay, this structure as what you see over here. All right, and this sequence here, PDOR, PSOR, everything is written the same sequence as how they appear in the memory map. Okay, so in the memory map, okay, we saw that this is the sequence PDOR, PSOR, and so on. So we follow that same sequence, okay, in the header file, okay, when we define the structure. Alright, so that is the definition of all the registers inside the header file already given to us. So all the peripherals that we are going to use has already everything defined. Okay, so all the GPIO definitions, so there's a question on the GPIO definitions. Okay, so it's automatically split into this file. So we do not need to redefine it in our main C file. Okay, we can just make use of the definitions already there in this this MKL header file. All right. Now another thing that we are using quite often is this idea of a structure pointer. Okay, so if you see down here, what we are doing is we will define a base. So in this case, this is port A base. All right, and port A base is this address. This address we get from where? This address we get from the memory map of the hardware design, okay, which is from the table just now we saw from the PDF file. Okay, so let me show you again. This address here. So this is the starting address of the port A. So every port has its own starting address. So we know that from the starting address, this is the sequence of all the registers. All right. So as long as we know the starting address of each of the GPIO ports, then we know the sequence of the registers that follow. Okay. So in the software, okay, in the header file, what they do is this technique here, where they declare a structure pointer. So when I look at this line over here, what am I doing? I'm defining this PTA or port A to be a GPIO type pointer. What is GPIO type? GPIO type is the structure that we just saw over here. Okay, so GPIO type is a structure, right? Because I define it as a structure, and this structure has all these registers, okay, all these variables. All right, but now I declare it as a pointer to a structure, and this pointer is pointing to this initial base address. All right, so when I want to access, for example, the PDOR register, I just put the base address, okay, and I say point to which particular register. Now this PDOR, okay, as you can see, is the first register. So automatically what you will do is you will access the PDOR as the first element in the structure. All right, if I say, for example, I want to access the PCOR or PSOR, for example, then that is an offset of 4, okay, because it is the next word after the PDOR. So it will automatically know which memory location to access based on the way the structure is defined. Okay, so that is how this sort of approach works for us. All right, so it is very elegant because as long as you know the base address and you declare a pointer to a structure, okay, and this structure already maps out all the registers for us, we can just use this approach here to access any particular register we want. All right, so this is actually also in the code. Okay, so let me show you where it is in the code. Okay, so this is where it is. Okay, so as you can see, so now they name it to GPIO base. All right, so you can use port A or GPIO A. I think both works fine. All right, so you can see the same thing. Here they declare GPIO base with the same address as what we saw just now, and they declare the pointer GPIO as pointing to the base address. All right, so this gives us a way to access all the registers in GPIO A using the structure pointer notation. Okay, and all of this you don't need to do. So like I said, it's all already in the header file. We just need to know how to use it correctly. Okay, so that will simplify our coding a lot. Okay, which I will show you in a while. Okay, so that is the technique of how we access hardware. So this is actually a very nice technique. If you learn how to use this correctly, I would say that in future when you deal with some other microcontroller, even if the header file is not given and you follow this approach, you will find it a lot more easier. It takes a lot of effort, definitely, the very first time you want to create this kind of structure and header file, but subsequently you will find that your life becomes very easy whenever you want to access anything. Okay. Okay, now another thing that we are also going to be doing quite often is this thing called the masking technique. All right, so we shift and mask. Okay, so this is also something that we have done before. All right, but let me just recap that correctly over here. Okay, so over here what we have is, for example, I give you this 32-bit value and I say I want to set bits 13 and 19. Okay, which is this and this. It is definitely not ideal to write it out in binary or even in hexadecimal. Okay, but even though I write in hexadecimal, it is easy. The problem is when I look at this value, okay, I still can't say immediately which bits are set. I still need to individually count the bits to know which bits are 1. All right. So even though hexadecimal makes our life easy, okay, but when you do the coding, all right, you want to make the code easily understandable. So one easy way is to do shifting. Okay, so when I do 1 shift left 19, basically means this 1 you can treat it as just 1, okay, with many zeros, okay, at the front. So you treat it as a 32-bit value, correct? So when I shift left to the 19, means I shift it okay, by 19 bits. So it will come all the way to the bit 19 position. All right. So similarly, when I shift left by 13, I will shift all the way to the left by 13. All right. So when I look at this, I will know that the value n, okay, the variable n will have a result such that bit position 19 and bit position 13 will both be set. Okay. Now another way of doing it is, of course, instead of hard coding the 19 and 13, you define it. Okay, so again, these are all techniques to just make your code even better, that is more readable and more well structured. So if I define it, then next time I know that, okay, green LED is in bit position 19 and yellow LED is in bit position 13. Okay, so this UL is basically just one of the coding things in the KL IDE. So UL stands for unsigned long. Okay, but you don't need to put it. Okay, even if you don't put it, it's still fine. Okay, so without the UL, it still works fine. It's just one of the sort of techniques that the KL IDE supports. All right. Now the even more better way of doing it is, okay, when you want to do specific actions, maybe multiple times, like in this case, we want to do this shifting for many bits, you can define what we call a mask. Okay, so when I define a mask, what happens? That means I'm saying that this mask function, all right, or a macro here, what it will do is whatever value I pass into x, okay, one will be shifted by that value. Okay, so when I call this function over here, what happens? I'm passing in mask green LED position, which is 19. Okay, so when I come here, it will be 1 shift left by 19. All right, so that will be for the left hand side, and for the right hand side, it will be 13. And then I perform the OR operation. Okay, so the OR operation, if you recall, okay, when I do an OR with the 0, nothing changes. When I do with OR with a 1, then the output becomes 1. Okay, so when I do an OR with a 0, nothing changes. As long as a 1, the output will become 1. So by doing this, okay, you make your code even better, correct? Because now I use a macro to define the mask function, and then I do the shifting, and then I do the OR operation. All right, so definitely, okay, if you look at it, all these are fine. All right, but definitely this last option here is the most ideal one, because you know that you need to do the shift operation, so you create a mask for that, and in this one line you can sort of see what you're trying to achieve. Okay, so try to improve the quality of the code that you're writing, okay, make it more readable and better, get through these exercises and this module here. Okay, so for arithmetic, there's a question here. For arithmetic operation, is the second option the best? Okay, so arithmetic operation, again, depends on what you are doing. Okay, if the operation is something that you need to do quite frequently, then you can do a macro for it. Okay, but if it's a one-off operation, then you can just put it in a single line also. Okay, so the question is easier if you write it in decimal. Okay, yeah, I mean, in some cases, the value that you are dealing with is easier if you look at it in the decimal value, correct? So if looking at it in decimal is easier, then you don't need to do all this. All right, but this is of course very useful when you are dealing with the register configuration. Okay, because when you deal with registers, you want to set specific bits, you want to clear specific bits, and so on. So you want to sort of understand how or which bit you're talking about. Okay, so these techniques here are all very good when you want the data to be represented in binary, all right, or you want to know the exact bits. Okay, but if you want to just look at the value in decimal representation, then you don't need to worry about this. Okay, so let's go on to this next slide. So this is actually from the next slide over here. Okay, so here basically we are talking about how to use the mask. Okay, so when we are using masks, all right, there are a few different ways in which you can use the mask. Okay, if I directly use the equal sign, I am overwriting any existing value in the variable n. If I do the OR operation, I am making sure that all the bits that are 1 here will be set. So all the bits that are 1 will be updated here in the output. Okay, if I do if I want to clear the bits, okay, in the mask, then I can do an AND with the complement. All right, so usually what we do is, if let's say I want to clear certain bits in the mask, okay, then I specify which bits and then I do the complement. And when I do the AND operation, I will clear the bits. Okay, so let me show you the example, then I think it's easier for us to relate to it. Okay, so let's look at this example here, okay, which is the actual C code, all right, of what we are trying to do here. Okay, so over here, what we have here is the LED1 and LED2 are first defined here, and the switch, and then we define the mask function. All right, now let's look at the first line over here. So in the first line over here, what am I doing? I'm saying mask LED1 position. So when I call this mask LED1 position, okay, what happens? I'm saying 1 shift left by 1. All right, so the bit 1, okay, which is originally like this, will shift left by 1. So it will become 0, 0, 1, 0. Okay, so this will be give me 0, 0, 1, 0. All right, then the next one, mask LED2 position. So it's the same thing. So it will be value 2. Sorry, 1 shift left by 2. So 0, 0, 0, 1. Okay, and shift left by 2. So 1, 2. So it will be 0, 1, 0, 0. All right, so after I shift, okay, it will be 0, 1, 0, 0. So that is the output of the two mask operation. All right, and then I perform the OR over here. Okay, so if I do the OR operation between this and this, what do I get? 0, 0, 1, 0 and 0, 1, 0, 0. When I do the OR operation, it will be 0, 1, 1, 0. Okay, 0, 1, 1, 0. And this value is doing a OR equal operation with the PDDR register of port A. Okay, so if you look back at your PDDR register, okay, so let's look at it from the data sheet. Okay, so the data sheet, okay, port A, PDDR. All right, so you can see that if I configure it with a 1, it is configured as output. Okay, so 1 is output, 0 is input. So what am I telling the port to do? That I want bit 1 and bit 2 of port A to be set as output. Okay, and the OR equal. Okay, so this OR equal means what? That means I do not change the other bits. Okay, do not change the other bits. Okay, I only am going to update these 2 bits only. Okay, so bit 1 and bit 2 will both be set for the PDDR register. So that will make it as output. Okay, so that is the first thing that we're doing. Okay, I know for some of you all this is very easy. All right, okay, so just bear with me for a while. Okay, so I'm just going through everything in detail only for this chapter. All right, because the first time you're looking at this style of coding, so I just want to make sure everybody is clear on what is happening. Okay, subsequent chapters, I will leave it to you to go through the details of this. Okay, so for the next one over here, let's look at what is happening. I'm doing the mask switch position. Okay, so the mask switch 1 position. So switch 1 position is 5. So that will be 1 shift left by 5. Okay, so let's do that here. Okay, so when I shift left by 5, what happens? So 1, 2, 3, 4, 5. All right, so the 1 comes here. Okay, and then after that I do a complement. Okay, I do a complement. That means I'm flipping all the bits. So when I do a complement, okay, what happens is I flip all the bits. So this one will become 1, 0, 1, 1, 1, 1, 1, and so on. Okay, I'm flipping all the bits. All right, and then what do? I do a AND equal operation with the PDDR register. Okay, so when I do an AND operation, okay, so for the AND equal, what is happening? When I AND with a 0, I clear the bit. When I AND with a 1, there is no change. All right, so you can look back at the AND truth table. When I AND with a 0, I will clear the bit. When I AND with a 1, there is no change. All right, so what is happening here is, since I AND bit 5 with a 0, bit 5 will now change to 0. The rest of the bits will not be changed. So bit 1 and bit 2, okay, which have been updated to 1 and 1, okay, from the earlier code, will still remain as 1 and 1. Okay, there will be no change, and the bit 5 will be cleared to be 0. All right, so that is what I'm doing over here. So at the end of these two lines, okay, at the end of these two lines, okay, what do you have in your PDDR register? Okay, what you have in your PDDR register is your bit 1 and bit 2 will be, so let me put it this way, 0, 1, 2, 3, 4, 5. Okay, so these are all the bits. We know that bit 1 will be 1, bit 2 will be 1, and bit 5 will be 0. Okay, so these are the 3 bit locations that we have configured, okay, with the 2 lines, okay, for the PDDR register. So we know that bit position 1 and 2, which is LED, is output, and bit position 5 is 0, which means it's input. Okay, so that is the first 2 lines over here. Okay, so as you can see, by using the mask and the definition and everything, it makes your code easier, correct? And by using the OR equal or AND equal, you are making sure that only those particular bits are configured, okay, and you do not change the rest. Okay, this next line over here, mask LED2 position. Okay, so LED2 position is 2. So when I shift, I'll get this. So I'll get 0, 1, 0, 0, which is this over here. And I'm taking this value and writing it directly to the PDOR register. Okay, and what is PDOR register? It's a port data output register. Okay, so when I write to the port data output register, whatever value I write here will automatically go there. So 1 will be 1, 0 will be 0. So in this case, what am I doing? The LED in the bit position 2. So this is actually LED 2, and this is turn off LED 1. Okay, because I'm turning on LED 2 and turning off LED 1. Okay, so these are the 2 bits we are changing that affect the LED. Okay, so that will be the default setting. Okay, the LED 2 is on and LED 1 is off. Okay, now in the loop over here, what are we doing? Okay, so if you look at this loop over here, we are first trying to do a check with the port A PDIR with the mask switch 1 position. So mask switch 1 position means I'm basically taking the bit 5, okay, which is this value over here. Okay, so when I read port A PDIR, so port A PDIR means I want to read port A, but I want to read the input register. That means I'm taking the bits that are configured as inputs. Okay, so when I read this register, PDIR register, okay, it is the full 32 bits. Okay, the full 32 bits. But what I'm interested in is only the bit 5. Okay, because the bit 5 is the one that's connected to the switch. So what I do is I do a mask. So in the mask, what I have is only the bit 5 is 1. Okay, this is bit 5. Okay, so when I do an AND operation here, what happened? The output result is only the value in bit 5. Okay, which will either be either 1 or 0, depending on whether the switch is pressed or not. Okay, so I'm only interested in this. Okay, everything else will be 0. Okay, only the bit 5 value will be the value depending on the switch. Okay, so if the switch, so if I read a value of 1, so if this gives me a value of 1, so the switch is not pressed, okay, then I keep the LED2 switched on. If the switch is pressed, then I switch on LED 1. Okay, so that is basically what this code is doing. All right, so if you look at it, okay, the use of the pointer to the structure and the mask, okay, makes things quite easy for us. Okay, as long as you know how to use this correctly in your code. Okay, so does anybody have any questions about this over here, this code over here? Okay, so these are things you will see very often in this whole module. This pointers to structure, the masking, the bit flipping and shifting and all these things. Okay, you will see it almost every class. Okay, so you must be comfortable with all of this style of coding. Okay, so let's move on first. Okay, along the way, you have questions, you can always ask me. Okay, so let's see. Okay, so let me just talk about this clocking logic and then we'll go for a break. Okay, so by default, okay, if you recall your Arduino Uno, we talked about power consumption and how to save power. All right, I think in EBP2. Okay, and if you recall, there is this register called power reduction register. Okay, in the Arduino Uno, where you can choose to individually switch off the subsystem. So I can switch off timer 1, I can switch off ADC, and so on. Okay, so that is the register to configure or switch off the clock to those peripherals. But by default, everything is on. Okay, and then you can switch it off. Okay, but the KL25Z is a bit different. Okay, by default, many things are off. Okay, that means many subsystems do not have any clock by default. All right, what you need to do is you need to manually switch it on. Okay, so this is also important because you may write all the code, you know, everything seems correct, but it doesn't work because you did not switch on the power to the subsystem. Okay, so different subsystems have different registers to switch it on. All right, so that is where again you need to look back at the data sheet. So for the GPIO, okay, we have this register called the SCGC5. Okay, SCGC5. So let me show you over here in the data sheet. Okay, so I'll just do a search here, SCGC. Okay. Okay. Yeah, so this is the SCGC5 register. Okay, so this is basically the so there are a few different SCGC5 registers or SCGC registers. Okay, and different registers are used for different clocking. So this register is specifically for a few things. Okay, and this is for all the ports that we have. So for all the ports A, B, C, D, E, okay, you need to come to this register and put a 1. Okay, so for example, if I want to switch on port A, I need to come here and put a 1 to that particular bit, then the clock is enabled. Okay, so that is what is shown here. Okay, and since the port A is in bit position 9, all right, okay, you need to do this. Okay, but again, that is also defined for us in the header file. So there is already a definition of where the port A bit position is. Okay, so you can just use this SIN SCGC5 or equals port A mask and you will switch it on. All right. Okay, in the code, okay, there is actually something that they do here is a bit interesting. Okay, where they do a shift and a mask, all right, for the value. Okay, again, this is not really necessary. Okay, but I will talk about a similar thing later when you do the port multiplexing. Okay, but for now you can take it that as long as I do this line, okay, is enough to switch on the clock. Okay, okay, so maybe I think now is a good time to go for a break. All right, so let's go for a 10 minutes break. Okay, when we come back, we will look at the remaining slides, and then I will again look back at the actual code, all right, for the lab and how it is going to be when you run it this Friday. Okay, so let's go for a 10 minutes break. Okay, if you have other questions, you can put it in the chat first. Okay, later when I come back, I will address those questions. Okay, so just go for a break. I'll see you back here at now is 10:55, so 11:05 we come back. Okay, so I'll see you in a while. Okay, so let's continue. Okay, so far what we saw was all the configuration, okay, to configure the input or output and to write specific values to it. All right, but if you recall just now, we mentioned that every pin, okay, is actually multiplexed with a lot of other functionalities. Okay, so one of it may be GPIO, but the rest of the functionality could be a timer, a PWM, or serial interface, or anything like that. Okay, so there's a lot of other functionality that is multiplexed with. So we need to be able to select the correct function that we want. Okay, and that is in this register called the PCR. Okay, pin control register. All right, so this is the register. Now, if you look at this register, okay, this pin control register is an individual register for each pin in the port. So it is not a global setting for the whole port. It is an individual setting. All right. So and at the same time, if you look here, you can see that for the multiplexing option, which is this 3 bits here, 8, 9, and 10. Okay. So for 3 bits, you have this 8 different values over here. Okay, so for these 8 different values, the actual one depends on a table over here. Okay, the multiplexing table. Okay, so let's look at the register and the table to try to understand how to make sense of it. All right. So if I go back to my data sheet now, all right. So let's first look at the PCR register. Okay, so this is the PCR register. Okay, so this, as you can see, is port X PCRN, where X is any of the ports. Okay, it means A, B, C, D, E, and N is the actual pin number. It means PCR for pin 0, pin 1, pin 2, and so on. Okay, so it's all for individual pins. All right, so this is the register. Okay, so of course there are other things here. For now, we will look only at the bits 8, 9, and 10. Okay, bits 8, 9, and 10, which are used for the multiplexing. All right, so if I look at these 3 bits here, 8, 9, and 10, okay, the value that I put in those 3 bits, okay, in this pin marks control gives me these different options. Okay, so in this case, you can see the alternative 1, that means 1 is GPIO. Okay, so for all of the PCR registers, the moment I put it as 001, it is automatically GPIO. Okay, but at the same time, we have all these other alternative options which are chip specific. So how do I know which functionality it maps to? All right, because I know the option 1 means it's GPIO, but how do I know the rest? Okay, so for that, we need to look back at the overall multiplexing table. Okay, so if you look back at your chapters and you go to this chapter 10, signal multiplexing and signal description, okay, you can scroll down a bit and you'll come to this very big table, okay, which is the pinout. Okay, signal multiplexing and pin assignments. Okay, so for example, okay, now we are talking about, let's say, port A pin 1. All right, this is port A pin 1. Okay, so you can see that this first odd 1, okay, is the GPIO, okay, port A1. Then alternative 2 is serial receiver. Alternative 3 is the timer 2, and so on. Okay, so for every pin, okay, the option 1 is always the GPIO option, but the rest of the option again depends on how you want to configure it. All right, and another interesting thing, okay, you will see is the same feature may appear as option in more than one pin. Okay, what do I mean by that? So if you see down here, this timer 2, okay, for example, when we cover timer 2, we will look at this, but what I want to show you is that this timer 2 channel 0 appears as an alternative option for port A pin 1. Okay, at the same time, timer 2 channel 0 also appears here as an alternative option for port E pin 22. Okay, so that is what I mean by the same peripheral option may appear in more than one pin. Okay, so you have options. You're not limited to that particular pin alone. You may look around for other options, other pins to use if I want to make use of that same peripheral. Okay, so you need to sort of look at this table very carefully. All right, when you are building up your project, okay, and you want to decide which UART to use, which timer to use, which GPIO to use, and so on. Okay, at the same time, there are also some things that you should avoid, okay, which I will talk about also along the way. All right, certain pins that you should avoid to prevent damaging the pin in any way or damaging the board in any way. Okay, so that is basically the multiplexing option with the PCR register. Okay, so the PCR register is again extracted out in the header file for us, and it is done using the built-in macros. Okay, so let me explore and show you this in a bit more detail over here, so you understand how it works. So this macro definition is also inside your header file. Okay, so if you go back to the header file here, okay, so this PCR mux definition is here. Okay, so I'm just going to explain to you how this works. Subsequently, all the future mux or masking have the same concept behind it. All right, so if you understand this once, the rest of it becomes easy. All right, so let's look at what is happening here. So when I look at this port PCR mux, okay, I pass in a value x. Okay, so what will I do with this x? So this x value, first I will shift it to the left by mux shift. All right, so this, what is this x? So this x value is the alternative option that you want. Okay, so in our case, what do we want? We want to make sure the mux option is 1, right? Because 1 is GPIO. So let's assume that now I pass in a value of 1. Okay, so the 1 comes here. So what will I do with this 1? I will shift it to the left by PCR mux shift, which is 8. Okay, so let's look at that. So when I take the value 1 and shift it left by 8, where will it come to? Okay, it will come here where these bits are all the lower 8 bits, and it will come here. Okay, so if I label the numbers, it will be from 0 to 7, and this will be the bit 8 here, 8, 9, and 10. Okay, so this value 1 will come over here. Okay, that's the first thing. We're shifting that value x to the left by 8. Okay, so from bit position 0, you will come to bit position 8. All right, now after that, what will happen? I am doing an AND with the mux mask value. What is the mask value? This. Okay, so if I were to put out the mask value over here, it is basically 0, 0, 0, 0, 0, 0, 0, 0, then over here it will be 1 1 1 because 7 is 0 1 1 1. Okay, so I do a AND operation over here. So I do an AND operation here. What am I basically trying to do? I'm just trying to extract out these 3 bits. Okay, the bits in position 8, 9, and 10. Okay, that is what the AND with the mask is doing. Okay, and I take this value and then I can update my PCR register. Okay, so that is basically what this PCR mux macro is trying to do for me. Okay, I pass in the value, okay, and that value is first shifted to the correct position. So the correct position is from bit 8 onwards. Okay, and after I shift to the correct position, I just want to extract the 3 bits, which is bit 8, bit 9, bit 10, because those are the 3 bits used for the multiplexing decision. Okay, and I do that by doing the AND with the mask. And once I get that, I can do the update to the actual register value. Okay, so that is basically how this macro works. Okay, so if I look at this example here, okay, so let me put this. Okay, so let me just show you this one example, how I make use of the mask. So now we understand how this mask, this mux macro works. Okay, now how can I apply it? How can I apply it correctly? So to apply it correctly is always a 2-step process. The first step is you clear the bits. And then the second step is you update the bits. Okay, so let's look at the first step. The first step basically is the AND with the port PCR mux mask, but with the complement of it. Okay, so what am I doing? So this mux mask is what value? Is this 0x700. Okay, so this is 0x700. So in terms of binary, it is 0000 0000 111, then all the rest is 0. Okay, and now I say I want to do a complement of it. So I do a complement of it, it will become 11000 and everything else is 1. Okay, and after I complement the AND operation. Okay, the AND operation with this. So when I do an AND with a 0, what happened? That means these 3 bits will be cleared. Okay, and I update it to which register? The port A pointing to the PCR register and the LED 1 position. So as what I mentioned just now, the PCR register is individual for each pin. So you need to specify which pin you're talking about. So is it pin 2, pin 3, pin 5, and so on. Okay, so now what I'm saying is for port A, pin 1 PCR register, I'm going to clear the 3 bits. Okay, clear the 3 bits that are used for the mux. Okay, why we want to clear the 3 bits? Because if there was any earlier configuration by somewhere else in the code, you want to clear it first. Okay, after I clear it, then the next step is I update it with the new value, and the new value is using the macro. So this is what we saw just now. So when I pass a 1 to it, what happens? The 1 gets shifted to here and do the AND operation. And finally, after I do the AND operation, then I do a OR here. So after I do this, what will happen? That means in this 3-bit position here, I will get a value of 0, 0, 1. Okay, which says that I want to use it as a GPIO operation. Okay, so of course, the very first time, it may still seem a bit confusing, okay, for some of you, but once you go through it one time, it will become easy after that. All right, so you just need to understand this style of coding. All right, how we are using the mux, the masking, the bitwise operations, the complements, everything. All right, so initially maybe it may take a while, but after that you will definitely find it quite easy. All right, so basically it's a 2-step process. I first clear the bits in the mux position of the register, and then I update it with the new value that I want. So in this case, 1 means is I want it to be a GPIO. Okay, so that is what is happening here. All right, and of course, as I mentioned, before anything, you need to enable the clock. Okay, so when you say you enable the clock to port A, means you are supplying the clock signal to the port A. Okay, then only port A is working. Okay, if you do not supply the clock, then port A is not functioning. Okay, which means that anything that you try to do with port A, you will not get updated. You need to make sure that the clock is first enabled before you do anything else with port A. Okay, so this next few slides is again just for some recap only. All right, in our case, all right, we are dealing with a controller, for example, up to 3.6 volts. Okay, so when you say it's 3.6 volts, what is considered 0, what is considered 1? Okay, so generally, okay, we can say that since our supply voltage is also 3.6 volt, okay, anything around 2.3, 2.4 to 3.6 is considered a logic 1. And anything from 0 volts all the way to around 1 volt is considered logic 0. Okay, again, this is just to sort of give you the idea that sometimes when you have floating voltages, all right, you might end up in a situation where it's undefined. So if it's the voltage that you supply is somewhere in this region, okay, then it is undefined, which means that the controller may interpret it as 1 or 0. Okay, so these are just some recap of your Ohm's law and things like that. Okay, which I think I will skip for now. All right. Okay, so in terms of the additional configuration, there are just 3 other bits that I just want to highlight here. One is the pull-up enable and pull-up select. All right, and why is this important? All right, because when I configure a signal as input, all right, okay, if I do not want to use an external pull-up resistor, I can actually enable the internal pull-up resistor or pull-down resistor. Okay, so in terms of switch configuration, okay, you can actually save a resistor by enabling the internal pull-up or pull-down, okay, depending on how you want to configure. All right, so that is one of the features. The other one is high drive strength. All right, this is again just another option. Okay, if you want that particular pin to provide more current. Okay, but in our case, we won't need to use this because we are already having a external motor driver, okay, to drive our motors. So that extra drive that we need comes from that. Okay, so let's have a quick look at lab 2, all right, and understand what we need to do, okay, for this week. Okay, so let me bring up the lab 2 manual here first. Okay. Okay, so for lab 2, okay, which is what we're going to do this week. Okay, so before we start, I hope you saw the announcement that for now, we don't need to have work from home arrangements. All right, again, this is for now. Okay, hopefully it lasts. Okay, that means all of you can come to the lab without any restriction. All right, so as long as you show the green pass, okay, so everybody needs to show the green pass, all right, which means you have to be vaccinated and you have to have done your weekly ART test, all right, okay, then you can come to the lab, so there's no restriction on that. Okay, so another thing I also want to highlight is I think I've been receiving quite a few emails from students who say that they have been identified as a close contact of a confirmed case, and they are asked to be isolated and things like that. All right. Okay. So basically, if you look at the current guidelines, all right, if you are considered as a close contact, you fall under protocol 3. Okay, and protocol 3 basically says that you are still allowed to go out if you do a daily ART test. Okay, until that period is over. Okay, but if you yourself feel that maybe you do not want to take the risk, you know, in case you spread to anybody, okay, and you want to work remotely, is also fine. Okay, so I mean, I'm just talking for this module alone. I'm not sure about other modules how the module coordinator is going to look at it. Okay, but for this 2271, if you're supposed to come to the lab, but you are again identified as close contact and you think you do not want to come, you can just log into the Zoom session and work remotely with your team. Okay, so I'm fine with that. So if you want to come, just make sure you have done the daily ART test, okay, as per the protocol. If you want to work remotely, just update the TA and inform your team members. Okay, so either way, it's fine for me. Okay, so for this lab 2, okay, we are going to go through the whole process of how to create a new project. Okay, and in this project, we are going to again go step by step. Okay, what are all the files, the header files, the libraries, everything you need to include. Okay, so you just follow through exactly as what is outlined here. In fact, even before you come to the lab, you can actually do it already. Okay, and after that, you just need to download the code. Okay, now so the objective of this lab is to control the three the RGB LED on the board. Okay, so let's take a look at the RGB LED and the board in particular. So there is another data sheet actually uploaded as well. Okay, so that is sort of summary of the Freedom board. Okay, so there's two data sheet. One is the actual microcontroller data sheet, which is the very detailed one. The other is just the KL25Z, the whole board itself. So this one is a bit of a summary where they just give you an overview of the hardware and the software and everything. Okay, so of course here they give you the details of some the connections, the features it has, and so on. All right, so that part you can have a look. Okay, so what I want to focus on is on the this part, RGB LED feature. Okay, so if you look at this RGB LED feature, okay, what can you observe? Okay, so you see that it is a single LED. All right, and look here. Now, can you tell me these three LEDs, are they considered active high or active low based on the design over here? Are the RGB LEDs configured to be active high or active low? Okay, so it's correct, it's active low. Okay, and how do you know it's active low? Basically, you can see that all the anodes, okay, all the anodes are connected together to the positive 3 volt 3, that means 3.3 volt. Okay, and the cathodes are the one that are connected to the individual ports. Okay, the cathodes are the one connected to the individual ports, whereas the anodes are all connected to a single 3.3 volt. Okay, so to turn on any of the LEDs, I need to put a 0, then the LED will light up. Okay, if I put a 1, the LED will switch off. Put a 0, it will light up. Okay, so that is why we say this is an active low configuration for the RGB LED. Okay, so what we want to do, okay, for the lab is we want to control the three LEDs. So it is port B18, port B19, and port D pin 1. Okay, so the code is already given here. Okay, so let's just have a look at the code and make sense of it. Okay, so let me open up the code here. So this is the same code is also given to you. Okay, so let me extract it out here. Okay, so you can see here that the three ports are the port B, pin 18, 20, and port D1. Okay, so for that, you need to first declare here. So you need to have some definition to say which LED, which number, and so on. All right. Then subsequently, all right, in your init GPIO function, okay, first we want to enable the clock. Okay, like I said, you have to make sure the clock is enabled before you do anything else. And since I'm using port B and port D, I need to switch on both port B and port D. Okay, so that's the first thing that we need to do. Okay, after that, we want to configure the multiplexer settings to make sure all three function as GPIO. So this one, I think we just saw. All right, so for this, it's the same as just now. We first clear the mux bit. So the first step is, okay, the first step is clear the mux bits. Okay, and then you update it with the new value. Okay, so that is what we discussed just now. So we do it for all three bits. Okay, 2 for port B, 1 for port D. Okay, once that is done, you configure them as GPIO, then we can set the direction. So in this case, all of them are output. So I set all of them to be 1. All right, so that is basically the init GPIO function. So once you do this, you have already configured them to operate in the GPIO mode, okay, to control the LED. Okay, and what is the objective here in your lab? Okay, you're supposed to write your code to achieve the objective of lighting up the RGB LED one color at a time. That means red, green, blue, red, green, blue, and so on. Okay, so let's so how you want to do it is up to you. All right, what I would suggest is to have some functions, all right, to map and control the LED based on how you want it. So for example, you may have a function to off all the RGB LED, you may have a function to control them to switch on individually depending on which color you specify and so on. All right, okay, in the Luminous I also added this function as a C file. Okay, it's already in the Luminous. So this is just a simple delay function. Okay, it is not specifically 1 second or half a second or anything. Okay, it's just a simple delay function which you can call to make sure you can visualize that blinking effect. All right, if you don't have this, then all the LEDs will switch so fast it will look as white light. All right, and inside your main function you can just call it in a loop to go through a sequence. Okay, so let me just show you, okay, how this code works. Okay, so of course after you finish everything, you build your code. Okay, if there are errors, you fix the errors, and if not, you can go ahead to go into debug mode. Okay, so I bring out my board here. Okay, so if I run my code now, okay, you can see that the LED starts blinking. All right, so basically I just control the LED to be on at any point in time. Only one LED is on. Okay, so of course you want to slow it down, you always put a breakpoint. Okay, so for example now I put a breakpoint in my delay. Okay, so now it stopped at red. Okay, then the next time it is green and then blue and so on. Okay, so the objective of the lab, okay, this week's lab is just to give you the idea of going through and creating your own project and writing some simple driver code for your LED. And all of this code is very important because, like I said, everything is progressive. Okay, so whatever you're doing each week, you will have to sort of rely on it later on. Okay, when you're putting everything together in your project. Okay, so that is why I emphasize here that you must try to develop, okay, good reusable code. Okay, because if you try to hard code everything, okay, with fixed values and so on, of course it will work. Okay, but later on when you are trying to work on your project, then you realize that you have to make a lot of changes. Okay, so try to make your code more reusable. That means things that can be broken up into functions, where it gives you more flexibility. I think that will be good. Okay, so when you want to use it again in the subsequent labs, it's easy. Okay, so again, it's up to you how you want to decide. So for example, you can have one function to on, one function to off. Okay, if you don't want to use, in my case, I use PCR register because PCR is immediately to clear the bit. Okay, so if I clear, I set it, if I switch on the LED. If you want to use PDOR, is also fine. Okay, so it's up to you to decide how you want to do it. Okay, so you don't need to follow your friend's example or whatever. And even within the same group, each of you can have your own implementation and you can just try it out. Okay, just to see how each one of it works. All right, and for this studio, you don't need to solder it. You don't need any of the header pins for this lab too. So even if you haven't soldered, you can still do it. All right. So this is basically the objective of this week's lab. Okay, in the last part, I just introduce you to the concept of the clock. All right, so we have a default clock setting, okay, of the board, which is actually at 20.97152 megahertz. So this is basically the default setting when you first create any new project. Okay, but I also give you the option of how you can switch to a higher clock, okay, of 48 megahertz. All right, again, this is just to give you the idea that, okay, you don't need to stick to one particular clock. You can always change it if you want to. All right, so it's a good starting point to get you introduced to the clock and the concept. Okay, so that is what you're going to be doing this Friday. Okay, so before we end, next week is your Chinese New Year holiday. Okay, it's Chinese New Year holiday, but we of course we're losing a lecture because of that. All right, but because we are already losing 1 week. Okay, we are already losing 1 week because week 13 is not usable for us. All right, so another week, if you lose, is going to be quite impact. All right, so what I will plan to do is for next week, I will be releasing a e-lecture, which is basically I will reuse last semester's lecture. Okay, the same topic on the interrupts. All right, so the concept of interrupts, I think, is not new to you. Okay, you have seen it before. So the reason why I want to do it this way is so that when you, for next Friday, the lab, you know what to do. All right, which is on the interrupts. All right. So that is basically how we're going to handle next week. All right. So I will be releasing the e-lecture. Okay. So run through that lecture, and after that, you should be able to handle the lab. All right. So with that, I think it will be easier, and you won't fall back too behind. Okay. So let's stick with this plan first. If I think of any other better solution, I will let you all know. All right. Yeah. So for now, that is how we'll do it. So please come to the lab this Friday. All right, and then we can try out this lab too. All right. If you have gone through the e-lecture for the interrupts, you can also go ahead to try lab 3 as well. Okay. So I'll upload everything this week. Okay. So if you want, you can try it this week or you can try it next week. Okay, and I'll also advise you on this week's Friday which are the pins you need to solder. Okay, for lab 3, you need to have one of the header pins soldered. Okay, so I will again advise you in the lab which one you need to get soldered, so you know how to run lab 3. Okay, so that's all I have for today. If you have any questions, you can stay back and ask me. Okay, if not, I'll see you all on Friday.